I'm Thomas Perisini. I'm general co-chair of the conference, and I really would like to welcome you all to this event, and welcome to sunny and hot London. Seems incredible, but it is. So I will just say very few things about what our conference will be, and then I will give the floor to our chair of the International Program Committee, Professor Sarah Spurgeon from ICL, and she will introduce our first plenary speaker, and it will be a very exciting talk. So just a few numbers very quickly. We received over 520 papers. Of them, 370 were accepted. And so you are going to see that the program is organized in 52 sessions scheduled over the 3 days. We do have 4 plenary speakers, 4 semi-plenary speakers, and an additional plenary speaker, which is the European Control Awardee. Okay, and that will be on Friday. Also, we have 5 tutorial sessions, and we had 4 workshops that were very successful yesterday. And I would like to ask you for your understanding and patience, because that will be the first major conference in control in a truly hybrid format, which has a lot of challenges, but it's also opened up a lot of opportunities for people that couldn't be able to attend for various reasons to enjoy the technical quality of the talks that we have and everything else. With that, thank you for coming. And I would like to introduce Professor Sarah Spurgeon from UCL, and the floor is yours.
Thank you very much indeed, Thomas. And I'd really like to add my welcome to Thomas's welcome to you all. It's great to be back with colleagues at ECC, and it's wonderful to have the privilege of hosting this together in London. Now, my job this morning is to chair the plenary of Sandra Hirche. Sandra really needs no introduction, I think, in our community. She holds the Technical University of Munich Liesel Beckmann Distinguished Professorship, and since 2013 has been chair in information-oriented control in the Faculty of Electrical and Computer Engineering at the same institution. Her research interests include learning, cooperative and network control, with applications in human-robot interaction, multi-robot systems, and general robotics. She's extremely well published, and her technical work has received many plaudits, including Best Paper Awards of the IEEE World Haptics and IFAC Conference on Maneuvering and Control of Marine Craft, Outstanding Student Paper Awards at the IEEE Conference and the CDC. She's also been awarded with an ERC starting grant, and latterly in 2009 with a follow-up consolidator grant on safe data-driven control for human-centric systems. Sandra is a fellow of the IEEE, and she's well known for her many contributions to service across IEEE, IFAC, and UCA. And it's a great honor to welcome her for our first plenary session of this ECC, Control for Personalized Robotic Rehabilitation and Assistance. Sandra.
So first of all, thank you very much, Sarah, for the very kind introduction. And of course, also, I would like to thank the organizers for inviting me and for giving me the chance to present our work here at ECC 2022. So fundamentally, it's not working. Okay. Brief stop. So fundamentally, this talk will be about online learning control with guarantees. Yet the concrete research questions and the results I present today, they are driven and guided by the application in robotic rehabilitation and assistance. And this is considered as one of the enabling technologies to master the grand societal challenge of prolonged independent living at a high quality. But before I start, I would really like to acknowledge the team that contributed to the results. So all students, past and current PhD candidates, postdocs, and also collaborators, and of course also the funding agency who supported this research. In order to understand the fundamental challenges that arise for control in the context of robotic rehabilitation and assistance, let's have a look at the particular example of stroke. Stroke is the major cause for long-term adult disability in the world. And the majority of survivors, they suffer motor disabilities. And it's well known from clinical evidence that they would benefit rehabilitation. The rehabilitation itself should directly start after the incident and continue up to 18 months after the incident, because that's the window of neuroplasticity, where things in the brain still change. Now, in order to realize such a continuum of care, apparently we need advancement in robotic rehabilitation and assistive technologies. So looking more closely at stroke symptoms, one of the great challenges is the high variability of those symptoms between patients, but also over the whole journey of rehabilitation. And in particular, the motion pattern and dynamics, they vary greatly here as indicated by those different personas. And you see a typical symptom here where a person suffers from weakness in the upper limb and also a reduced precision in motion. So grasping becomes very difficult and can only be accomplished by compensatory motions that are undesired. From a medical point of view, it's quite well acknowledged that the therapy should be tailored to the individual person and situation. So it requires a personalized approach. There has been great progress on the hardware side in recent years in terms of devices, in particular with respect to the sensing and actuation capabilities. And it includes, for example, exoskeletons, as you see here on the upper left, where you see a full powered exoskeleton for clinical use, or on the lower left, soft robotic exoskeleton for the hand. And it goes towards even functional electrical stimulation, as you see on the right. They are suitable for the different sensory motor programs for rehabilitation, starting from resistance training to functional training up to assistance activities of daily living. So obviously, because there's direct contact between the device, so the physical machine, and the human, safety is one of the most critical concerns. And this has to be addressed on several levels. So we require also from the control system strong performance guarantees. Also, there has been a trend towards wearable and mobile systems because they facilitate rehabilitation and assistance at home. And this is also pushed by soft robotic technologies, which themselves are quite difficult to control. But also the variability and mobility, they induce resource constraints that has to be considered when doing the control design. Now, let's have a brief look at the control tasks that are typical within rehabilitation settings. And where in particular also the personalization of control plays a significant role. So the control architecture that you see here is taken from our Horizon 2020 project, Rehab, which aims to develop technologies for the rehabilitation and assistance of stroke patients with upper limb disabilities. And you see there are 3 layers considered, the low level, mid level, and high level control. And in the low level control, basically the main task is tracking control, for example, for an exoskeleton or also functional electrical stimulation. And one of the things you should observe here that the human is directly coupled to the device. So it really influences significantly the dynamics that you need to control. On the mid-level, the mid-level is responsible for the sharing of the control between the human and the machine. And it's also responsible for recognizing the intention to do that in an anticipative way. And again, intention recognition, you need to have a motion model of the specific human, which is highly variable and uncertain a priori, or unknown a priori even. And finally, the high-level control basically decides on the context, the goals of the human, and also sets the assistance task and general rehabilitation program. So we see that we have high uncertainty due to the unknown and difficult to model human dynamics, including the motion intention, motion planning, and we require adaptation to the individual user. But this adaptation has not only to be safe, but also fast, because usability and fast calibration times are an essential asset in order to deploy this technology. So bringing that to a more general level, the required safety and performance guarantees are seriously challenged by the uncertainty, and the variability comes together with sparse data regimes, because we require a high level of personalization. So we initially don't know exactly, or we don't have enough data about a particular person. On the other hand, the decision-making in milliseconds in robots, and also the desirable autonomous adaptation capabilities are challenged by the constrained resources. So efficiency is another important aspect. And in this talk, I will present an approach for robust online learning control, and we'll particularly look into the aspects of guarantees, and also I present ideas to improve the efficiency of the approaches. When it comes to learning control, then there are a number of design choices to make. The first one is regarding what is learned. So we distinguish between model-free architectures and model-based architectures. And in a model-free architecture, directly the policy is learned from performance observations of the system interacting with the environment, while in model-based architecture, first the process model is learned, and in the second step, a control policy is derived based on that. We opt here for a model-based control architecture. First of all, it's better interpretable for human experts and medical diagnostics. And furthermore, it also has been shown that model-based control is much more efficient in terms of the required data that you need than model-free approaches, which of course also is very beneficial when we think about our very patient-specific models. The second design question, or the choice we have to make, is what kind of approach we use to learn the process model. And there are a number of approaches available, from parametric approaches to deep neural networks to non-parametric approaches such as Gaussian processes. Here in this talk, we'll particularly focus on Gaussian processes, first of all, because they have an explicit and rigorous uncertainty quantification that will turn out quite beneficial for the robustness guarantees we'd like to give. And secondly, also, they turn out to be quite generalizable in this light of sparse data. So let's first give some background on Gaussian processes. Gaussian processes, or brief GPs, are a Bayesian machine learning technique. They allow flexible modeling of nonlinear functions. They represent a distribution over functions. And the basis for it are the noisy observations of the unknown function f, and also the prior, particular prior variance, which depends on a kernel with its hyperparameters. The pointwise prediction now, conditioned on the training data that we have, is again a Gaussian variable that is characterized by a posterior mean and a posterior variance. And in this posterior variance, there is now a direct link between the data, training data quality and distribution, any uncertainty in the prediction. And you see that here in the shaded area, red shaded area. So this is the posterior variance, and far from training data, this posterior variance is high. So it gives high prediction uncertainty, and it's what we call epistemic uncertainty. Close to the, on the other hand, it also encodes the uncertainty due to the noise. So this is called aleatoric uncertainty. So here, this explicit measure of model uncertainty, plus also the high flexibility and generalization capabilities, made us choose Gaussian processes. One of the challenges in Gaussian processes is the computational complexity, which increases with the number of training data, and we'll address that in the second part of this talk. So, but first, let's think about performance guarantees in closed-loop control systems. And it turns out that many of the certificates can be expressed in terms of derivative conditions on a scalar function. For example, we think about stabilization via Lyapunov arguments, then corresponding Lyapunov function derivative needs to be negative definite. Similarly, for safety via set invariance, we require barrier function derivative to be positive definite. And the analysis now is rather straightforward if our closed loop dynamics is exactly known. The key question now is how an uncertain f affects the derivative conditions. And here in this talk, we'll focus on Lyapunov-like derivative conditions. So let's now consider an uncertain closed loop dynamics. And we assume that we can decompose our uncertain f into a nominal known part and an uncertain part. And a nominal known part contains all the prior physical knowledge that we have, and within the GP framework, also the posterior mean function, while the uncertain part contains the posterior variance. As a result, we can now directly write the uncertain derivative conditions as a composition of a nominal part and a uncertain part. So as we deal with safety critical systems, we consider the pessimism in the face of uncertainty paradigm and consider the worst case in terms of the derivative estimate, v dot pes, which is composed of a nominal part and the absolute value here of the uncertain part. Now, if this pessimistic estimate is negative, then we know we can guarantee robust convergence. So now, when we employ the Gaussian process to model this unknown part of the, or the uncertain part of the closed loop dynamics, then we will see that we can directly relate the uncertainty coming from the training data to the robustness certificate for the Lyapunov function derivative. And to this end, we exploit what's called the uniform quantification of uncertainty for a Gaussian process. And it can be shown that the error between the true function f and the posterior mean is bounded with high probability by a product of a scaling factor and a posterior standard deviation, which we, as we just saw, directly depends on the training data distribution and quality. So as a result, with this error bound, we can now uniformly bound the pessimistic Lyapunov function derivative over a complex set omega. And you see here in this term that the uncertainty now directly depends on the one hand on this posterior standard deviation coming from the Gaussian process and the data distribution, and the gradient of the Lyapunov function, which is related to the control task. So it depends both on the training data distribution quality, but also on the control task itself. And now we can use classical level set arguments to show the probabilistic convergence to a bounded set. Okay, and now I'd like to show you an example why it is important to consider really this epistemic uncertainty, so the uncertainty coming from limited training data. And to this end, we look here at an example of an inverted pendulum, which is stabilized by a feedback linearizing control law. And the dynamics or the model of the inverted pendulum is learned via Gaussian process from training data, and it's only the posterior mean is used in the model. And our nominal stability analysis now suggests that actually the controlled system is stable. Yet if we apply the controller now to the real system, then we see that actually the unstable equilibrium is not stabilized by this controller. And the question is why? And closer investigation shows that actually our training data are quite sparsely distributed. And in particular, they do not cover the quite essential area around the equilibrium that we want to stabilize. So it's really important to consider this epistemic uncertainty in the control design. In fact, if we had applied our robust analysis that we saw before, then we actually would have seen that with this kind of data distribution, we cannot show robust stability. In fact, we can show with a high probability that the equilibrium is unstable. And you see on the left-hand side, the state space of the pendulum, where in red, the pessimistic Lyapunov function derivative is positive with high probability, and in blue, it's negative. And you see there's a large area red around the equilibrium. If we change the data distribution and add more training data, as you see here on the right-hand side, then this red region becomes very small. And in fact, we can show ultimate boundedness. And as a more general result, we can show that for control affine systems where we do feedback linearization with a Gaussian process, that we achieve probabilistic convergence to a ball. And this ball is characterized on one hand by the control gain, but also directly by the data distribution here. And this is indicated here by the sigma bar. So as an intuitive message, you can say the more and better training data that of course need to be well distributed with respect to the control task, the smaller or the more tightened robust performance guarantees you can give. Okay, so far, we considered that our training data are basically given. So, however, in our highly uncertain conditions that are also very variable, this is not the case. And in this case, that calls for an approach where you do parallel learning and control. Now, in this online learning setting, the training data are continuously collected on the fly during the operation of the system. And our Gaussian process is continuously updated, leading to a essentially switching controller. And so the question now is, can we still translate our performance guarantees that we have to this case? And the answer is yes. So by employing a common Lyapunov function framework, and under the assumption that with more and better training data, the uncertainty is reduced, it's quite straightforward to see that the pessimistic Lyapunov function estimate becomes smaller. And so we can guarantee, again, convergence under the assumption. So whatever leads to a reduction of uncertainty in the training data will lead to a more tightened performance certificate. And we have, this is illustrated here in the inverted pendulum example, again, which essentially starts without any model. And you see that in the pessimistic Yakimov function derivative being initially still positive, and on the fly training data is collected here for resource and constraint. It's done in an event triggered fashion only if the pessimistic Lyapunov function derivative becomes too large. So, and we see, that the pendulum is stabilized. So, but now let's take a step back. So the key assumption the key result that we used for this robustness analysis came from the uniform quantification of the error. So the error bound from the Gaussian process. Yet turns out that this error bound is only valid if we are given the hyperparameters. Yet in a realistic setting, typically you just have training data. So there's no hyperparameters given. And in fact, it turns out when you do the classical hyperparameter training, which uses the log likelihood optimal set of hyperparameters, then in many applications you see that the Gaussian process or the variance, posterior variance, is overconfident. So by no means that is a suitable approach then for the safety critical systems. And thinking about it, the approach to use a log likelihood maximum version of the hyperparameters is essentially flawed, because in principle we forget all the uncertainty about the hyperparameters when we do this approach, and we ignore those hyperparameters that we didn't choose. So the idea is now to take also a Bayesian view on the training. So instead of choosing this log likelihood optimal set of hyperparameters, we take the 1 minus delta confidence region for the hyperparameters conditioned on the training data, and we use a conservative bound to basically compute the variance. So in the end, we get a new robust uniform error bound for unknown hyperparameters, which has essentially the same form as the original error bound that we saw before. We tested this error bound in several benchmark data sets. And here we present the results for the Sarkos arm data set, which is a 21-dimensional data set. And what we see is that we get the same excellent regression performance as one would expect, as likelihood optimal. But on the right hand, you see that our approach has a significant lower violation of the error bound. So with this novel hyperparameter training, we get a superior approach for really safety critical applications. So we apply that now in an online learning control approach to control Lagrangian systems. And here the control task is tracking. And we assume that part of the robot dynamics is unknown. So in our particular example of the exoskeletons that you see here in a simulation, we assume that the human impedance is unknown. And we use a classical approach to do such tracking control as computed torque control, which combines a parametric feed forward with a PD feedback control law. And when we just use the parametric control, the parametric model of the exoskeleton, then you see that we have a quite an unacceptable large error between the desired green trajectory and the executed red trajectory. We could now simply increase the gains. What happens then, of course, is that our noise gets amplified, measurement noise, and this results in a very unsmooth and therefore also for exoskeleton applications, unacceptable performance. Now, for comparison, when we do the online learning with the Gaussian process, then you see in the same setting, so we just add here to our parametric model a hybrid, the Gaussian process, which learns the residual and then called a hybrid model. And you see within a few steps, few sample steps, basically the human impedance is learned, and we achieve a high and robust performance. So what you don't see here, but we can also guarantee that the tracking error stays with high probability in a tube around this desired trajectory. And this tube even gets reduced the more training data you accumulate over the course of the training. So far, we considered epistemic uncertainty, so uncertainty coming from the limited training data only for the robustness certificate, so for the analysis. But I'd like to show in a very few and brief examples how it can be also beneficial to consider it in the control law itself, so to modulate the control and or the learning part. So now the control law does not only depend on the state, but also on this epistemic uncertainty. And the first example is about computer torque control. And here we increase the gain as a function of the posterior standard deviation. So the intuition is that in regions of less model confidence, you expect a higher error. So therefore, a high gain is needed to ensure good tracking. But on the other hand, in regions where you have a high prediction accuracy, you can tune down your feedback control law, and you are less sensitive to the measurement noise. And we can show for this approach the ultimate boundedness with high probability, and we further get improved tracking performance compared to just static gains, and much less sensitivity to noise compared to the approach that we saw with high gains computed torque. In our second example, we consider a control Lyapunov function approach, where in the Lyapunov function itself, we consider a risk measure. So it includes basically the posterior variance from the Gaussian process as a risk measure. And as a result, our where we apply that to a dynamic system, then as a control, then we see that the regions of low training data density are avoided. And you see here, for example, in this example for stabilization of an unstable equilibrium of a very nonlinear system, that we just had these black dots, so two trajectories as training data. And the result, when we apply the control Lyapunov function approach with the risk measure, starting from different initial conditions, that they try to be as fast or move as fast as possible, a state to the known areas of performance. So, and as a result, we get a risk-averse behavior with tightened performance guarantees. And finally, one application-oriented example from assistance. So where we use an intention-driven shared control for the haptic assistance, and basically the robot is supposed to support the human and identifies the human intention, takes the uncertainty about the human intention, and either has a more aggressive support or more cautious support, depending on the uncertainty about the movement intention of the human. And we did a user study. And indeed, this user study with many participants reveals that such a risk-sensitive optimal control approach for the assistance is much better in terms of the perceived helpfulness of the robot. And it leads to lower disagreement in terms of the interaction forces between the human and the robot. So those were the three examples I wanted to present. But of course, there are many other approaches, meanwhile, that use the epistemic uncertainty quantification from Gaussian process in the context of robust performance analysis, but also adaptive control. And this list should just show you that this fundamental idea and concept is applicable in conjunction with many model-based approaches that we know from our community. Okay, so I'm at the end of the first part of my talk, where it was about robust performance certificate, where we see that dependency on the available training data quality and distribution, and also that this translates to online learning. And the key message is that in particular, when you have safety critical application with sparse data, then it's really important to consider this epistemic uncertainty. Okay, so now the question is, how do we achieve computational efficiency for the operation of such online learning control schemes in resource-constrained platforms? And to this end, let's have a look at the challenge we are facing when we do online learning control. So as the system operates, there is a continuous stream of training data coming in. So then the model updating and prediction takes longer and longer time with larger and larger amounts of data, so that eventually the real-time constraint is violated. And for example, in robotic application, sampling frequency ranges between 1,000 and 5,000, even 5,000 hertz for force control. So we can easily talk about like tens of thousands of data samples within a second. Now, in particular, Gaussian processes are known for being computationally demanding, and the exact Gaussian process scales, for example, in terms of updating and prediction quadratically with the number of training data. So the current challenge is to develop efficient approaches to online learning, but of course, we still would like to inherit the performance guarantees that we've given before. So let's first think about what we mean by efficiency when it comes to learning-based control. And our interest is to guarantee a high closed loop performance, a guaranteed high closed loop performance, rather than just thinking about the predictive performance of the model itself. So the key question here is, how can we improve the balance or trade-off between certifiable performance and the computational complexity? And in Gaussian processes, or general non-parametric system, the computational complexity is directly tied to the number of training data. So, and this gives us two orthogonal directions to approach the problem. So the first thing, as we may think of, given a number of training samples, which are the most relevant ones, which would we select to improve certifiable performance? And this is a question of sample efficiency. The second direction is that we could ask, okay, given a number, for a given number of training data, how can we reduce the computational time in terms of prediction updating? And I will only briefly touch upon the sample efficiency here. So our results show that we can improve sample efficiency by learning in the right representation. So for example, in the representation of energy conserving system, on a manifold of energy conserving systems. And that also it's important to consider the control task in the selection of training data. So rather than the regression performance is not as important than really the control task itself, as you also saw already in the Lyapunov function, pessimistic Lyapunov function derivative. So for more details, I would like to refer you to our publications. Here I will talk about algorithmic efficiency. And so the question is, how can we do an efficient online learning for Gaussian processes? The idea is to apply a divide and conquer strategy, and instead of learning a large, one large single GP, we employ what we call a locally growing random tree of GPs, or brief log GP. And as the streaming data come in, the model is updated in terms of the kernel matrix and hyperparameters. But once a certain threshold for the training data is reached, we split the training data into two sets. And So we have now 2 local models and a division rule, which we'll discuss later. And as more data come in, so again, we split the model, and this comes, once the threshold is reached, eventually new leaf models develop. So this corresponds to a growing tree of local models. And with this iterative tree construction, we can show that the learning has a complexity of log n, so which is much better than the n squared that we had before. Now, after learning, let's look at prediction. And of course, the division rule itself significantly affects the efficiency of the prediction. So the idea is that we successively split the state space into regions corresponding to local models. And this means that the original data sets that we had assembled according to a probability distribution over the state space. And so this also means that the regions are shrinked. And so in terms of the prediction, some of the path, for example, the one to node 3 and node 4, no longer need to be considered in this, in this prediction. So they're pruned. And so this kind of shrinking active regions for those local models yields a prediction complexity of log square n, so also much better than the n squared that we had before. So in summary, we can learn with complexity of log n, predict with complexity of log square n, so we are much better than the exact GP. And here comes a cherry on the tree, on the cake. So we also can uniformly bound the prediction error for this kind of log GP construction in a similar way as for the original Gaussian process. And now the posterior standard deviation is only replaced by this red sum here. So we get computational efficiency without losing guarantees. And of course, we apply this in several benchmark data sets in an online learning setting with training samples reaching in the Sarkos data set from 45,000 samples to the electric data sets 2 million samples, and about in social media up to 77 dimensions. And we compared it to several existing alternatives for online Gaussian, efficient Gaussian process learning. And we see that we get a similar regression performance as our alternatives, but a much better update and prediction times. So in some cases, the order of magnitudes better. And of course, not to forget the guarantees we can give that all the other approaches do not provide. And you can find the code for that on our website. Okay, finally, I would like to present an approach that exploits this modular structure of Gaussian, of this log GP approach on locally resource constrained systems. So we achieved now a much better computational complexity, much lower, but when we look at the memory requirements for online learning, still we get a linearly increasing memory requirement for the log GP. And this outgrows the capabilities typically of wearable devices, where you really want to have very, very small devices on your limbs. So the idea now is to smartly offload the computations to some remote infrastructure. And to this end, we assume that we have a local log system with limited computational power. And it does use a the localized model, which is smaller than the original model of the log GP, to do the prediction. And it's connected over a communication channel with some computation infrastructure, so cloud, which essentially performs the data management. And the new training data, they are streamed into the cloud system, where the updating and the tree construction and everything takes place, the updating of the log GP. And based on the future reference trajectory and some reachability considerations, analysis, the most probable active models for the future are determined and sent back over the communication channel to the local memory, where it's then used in the local system. And so with this pure externalization, we get the same uniform error bound as for the log GP and analogous control performance. However, of course, when we consider communication limitations, such as bandwidth limitations and also time delay in a communication channel, then of course there's a trade-off between the achievable control performance and the communication and local memory constraints. So it determines how many localized active model you can store and how fine-grained they are essentially, and the limit communication bandwidth and delay decide on how fast you can actually change those localized models. And in principle, you can say that you see with increasing delay and decreasing bandwidth, a decreasing control performance. So again, we validated that in our tracking scenario with the exoskeleton, and on top you see the comparison in the tracking error between the log GP and what we call the network log GP, so that exploits this offloading. And at the lower part on the right-hand side, you see how the memory requirements increase. And you see that for log GP, it increased linearly, and with the network log GP, it stayed under the limit of 3K samples. And so here it's seen as again, and what you just saw, it's actually these tubes, these uncertainty tubes, where you can, with high probability, guarantee that the tracking error stays inside. So again, we have performance improvement, and we can even give guarantees about it despite those resource constraints. Okay, so with respect to algorithmic efficiency, we have seen that we can significantly reduce the computational complexity for Gaussian processes, and also may offload, by offloading it and exploiting this modular tree structure, you can do a lot of things in terms of a network log GP, but also, for example, distributing on several agents. That's maybe not relevant here, but there's a number of things you can do with that. And all with the performance guarantee, so we can now have an approach for online learning control that is also applicable in resource constrained safety critical systems. And finally, I would like to give you a flavor of the experimental validations we do. So here you will see a shared control scenario where we basically applied all the things we have seen so far. So the human dynamics residual is learned with an online log GP, and we wanted to test, in a user study how well the human perceives the adaptivity and whether it works at all. And the task here is an assistive setting where the control is shared between the humans, so it operates a haptic interface, and a control of tracking that you see here on the screen is shared between the human and the haptic device. So the voluntarily applied forces, they are learned by the Gaussian process, by the log GP, and used in a computer talk control scheme. And we compare now this online learning control versus an individually tuned PD control. And as I said, we have multiple subjects, all of course have different motor performance. All of them were even healthy, so but still have different motor dynamics and patterns. And we saw that actually we can guarantee a high performance for every user, because with the online GP setting, so the variance in terms of tracking, first of all, was better with the online GP, but also the variance between the user was much smaller with the online GP. So first of all, we could show that you can learn in real setting with 200 Hertz with this log GP, keeping the real-time constraints. And also we could show that fast adaptation really supports this individualized assistance. And maybe as an interesting note, it's really important how fast you learn. So if you learn not fast enough, then you will not see a beneficial effect. Because you, of course, have to also consider that there's a mutual learning taking place between the human and robots, which could become eventually unstable. Okay, I'm at the end of my talk. I've presented contributions for robust online learning control with guarantees for uncertain systems, and with the major aspects of really robust performance certificates and for efficiency for the application and resource constrained systems. And of course, while we motivated our approaches and techniques with our research in robotic rehabilitation and assistance, the fundamental results straightforwardly extend to other applications where, in particular, where safety plays an important role, robust performance, and also resource constraints, and of course, limited data. And finally, what I'd like to comment that, our results present, in our view, like first successful step towards development of a framework for trustworthy control for complex safety critical and human-centric systems. But of course, there are many more dimensions you need to look at, and also more problems that become interesting. And I just will name a few challenges. One is to do robust learning control with guarantees for system where the state space is largely unknown, for example, as in functional electric simulation, and where you only have high dimensional measurements. So to do kind of this perception-based learning control. Another very important aspect is how to transfer knowledge that you might have. So I mean, patient population is large, so you could think about how to exploit data that you have from other patients and what parts are transferable, and in particular, and also what is the trade-off with privacy constraints that are, of course, always a very important aspect to consider in the context of human-centric control. And finally, in integrating it with higher level control parts in terms of cognitive shared control, so integrating also the high level is one of the pressing challenges. And we believe that control community can actually contribute a lot with the rigorous understanding for the analysis, but also the systematic design of approaches. And with the help, of course, of neighboring disciplines such as machine learning, AI, and also in particular for human-centric systems, not to forget human sciences. And so with this, I would like to thank you for the attention, and thank you.